Thanks everyone for attending the 5th meeting of the Scientific Visualization Interest Group. All the past talks are being posted to YouTube. I'll attach a link in the chat window to the YouTube channel in case you haven't seen it before. Last week we had a sort of non-recorded session where a lot of the Janellians just talked about how we actually use Jeremy's Neuroglancer tool, and that was interesting preparation for this talk. For those who are at Janelia, you can visit the interest groups page at wiki.janelia.org. 2 weeks from now, Cyril Rossant will present DatoViz and VizPy 2, so a couple of really interesting visualization frameworks, particularly for those in the Python ecosystem. Today, I have the pleasure of introducing Jeremy Maitin-Shepard, the creator of Neuroglancer and also one of the lead developers for TensorStore. He's been a part of Viren Jain's great team at Google Research since 2015. And we've had the pleasure at Flying M side of collaborating him with for a number of years on Drosophila brain reconstructions, as has many people at Janelia, I think. And so since we're somewhat familiar with Jeremy, I'll just turn it over to him and let him talk about his great tool.
Thanks, Bill, for the introduction and for inviting me to this series. I'm assuming that the audience is mostly familiar with Neuroglancer, so I'm not going to go into a broad overview of it. But I will
Jeremy,
do is in general.
I think you might want to get a little closer to the mic. It might be that the audio from your side is a little bit low. I'm not sure if that is the case with other people. Yeah.
Yeah, let's see if I can increase.
If you can up the
volume. Okay, is that working better? How about that?
Yeah, that's
okay.
better.
Great. Okay, so I will. Yeah, so I'm not going to, give a broad overview of Neuroglancer, but I will give an overview of the sort of general Neuroglancer design principles and the architecture, and then go into some of the interesting challenges regarding GPU programming that are relevant to Neuroglancer, and then talk about some of the lessons that have been learned through its development history, and finally briefly touch on some future directions. One of the main design principles of Neuroglancer is, of course, performance. I think it's fair to say, if it didn't offer relatively good performance, it would be vastly less useful. And the way that we've tried to achieve this is through minimizing the amount of data manipulation that has to happen on the CPU and offloading to the GPU as much computation as possible. Because Neuroglancer is a web application implemented in JavaScript, CPU computation, although browsers do an admirable job at optimizing things, is still relatively expensive compared to a native program, whereas computation that happens on the GPU gets pretty well optimized by the shader compiler. And so that's sort of, for a web-based application like Neuroglancer, there's an additional benefit to trying to offload things to the GPU even more than a regular native application. Asynchronicity is another sort of key design principle at the core of Neuroglancer. Because it's a web-based application intended to work with data received from varied sources over the network, it was important that rendering and user interaction is never blocked by the availability of data or even metadata loading. And so instead, Neuroglancer is essentially designed to just always render or display whatever data is available, and robustly handle data that's not available, or even metadata that's not available. For example, if you open a saved Neuroglancer state, initially none of the metadata is available. And so as the metadata for the different data sources become available, Neuroglancer will begin to be able to render them. And so if only some of the layers metadata has loaded, then that's what will be rendered, and other layers just won't be rendered. But the rendering of the entire view is not blocked by some of the metadata being loaded. And so this, I think, it leads to an overall a nice user experience in terms of being able to sort of rapidly start to see some data as soon as you open the Neuroglancer link, and makes it robust to the possibility that some data sources may not be even available at all because the server is down or the data has gone away, and still being able to view what's available. In terms of the user interface, I've sort of tried to immerse the user in the data, and do that by keeping the UI controls relatively minimal and unobtrusive, relying on key commands more than in sort of key and mouse commands, rather than sort of a large palette of icons that might take up a lot of space. Along those lines, I've also tried to keep Neuroglancer fairly generic. It was actually, in large part, Neuroglancer was inspired by a demo of Big Data Viewer that Stefan Solfeld gave to me back in 2016 when I was visiting Genelia, and the specific idea of not having a preferred orientation for the data. A lot of viewers are very heavily oriented around viewing XY slices of data, whereas in Neuroglancer, while it can show XY cross sections, it can equally show arbitrary cross sections at oblique angles. And then more generally, I've tried to keep Neuroglancer free of a lot of domain-specific functionality. Rather than providing a set of fairly tailored tools to specific domains, I've tried to keep it fairly generic so that users can then hopefully adapt it to their use cases without the core tool becoming bogged down in a lot of domain-specific functionality where what might seem useful one year, then the next year is sort of a maintenance burden. Neuroglancer has basically relied on its JSON state, which is encoded in the URL as its primary API. This means that you can share the state by just sharing a link, and because this state gets encoded in links, backwards compatibility for this state representation has been paramount. And that certainly has been a challenge to maintain this backward compatibility over the years, as there's been major changes like moving from supporting only 3D multi-channel data sources to supporting arbitrary ND data sources. So it's certainly been sort of required some gymnastics to sort of migrate in sort of pretty major ways the internal representation, while still maintaining backwards compatibility of the state, and allowing these old states to be loaded in a new version of Neuroglancer. But because of how critical sharing of states and links has been to Neuroglancer's use, that was something that couldn't really be compromised. On the other hand, the internal APIs of Neuroglancer have not been kept stable. So I sort of see this as similar to the model used by the Linux kernel, where there's this the kernel system call API, which is the interface that users face to interact with the kernel. And that has remained a sort of an extreme stability guarantee that's offered with the kernel system call API, which has allowed old user space programs to run on newer versions of Linux, and it's also what allows the whole sort of containerization to work very well on Linux. But on the other hand, internal kernel APIs change fairly rapidly, and this allows the Linux kernel to be refactored and support new types of devices and so on without being bogged down by major backwards compatibility concerns. So finally, as I said before, I've tried with Neuroglancer not to sort of have it too heavily tailored to very specific use cases or proofreading tests, but instead try to make it really programmable. So one of the early forms of this was to allow users to customize the rendering of images and then later skeletons and annotations by using essentially little snippets of the OpenGL shader language. So this is actually quite, from an implementation perspective, quite simple to support because Neuroglancer itself is using the shader language to implement the GPU rendering. And so sort of, we could basically just leverage the existing shader compiler provided by the web browser to allow users to define their own custom rendering within a sort of framework that Neuroglancer provides. That was something relatively unique in Neuroglancer, I think, and saved us from having to sort of provide a lot of elaborate user interfaces for choosing colors or different min-max bounds or various ways of mapping the raw data to colors on the screen, and instead providing just a way for users to program that and do it arbitrarily. And then there's also been a Python API which allows users to interact directly with the viewer state, and likewise allows users to basically program their own custom annotation or proofreading tools while keeping all of that complexity out of the core of Neuroglancer itself. Another key design principle that's not so much Neuroglancer as a whole, but relates to the Neuroglancer pre-computed format and other formats like N5 and ZAR that are supported by Neuroglancer, is this idea of cloud-native data storage. Now, cloud-native, I guess, is a term that's used in various ways, but the way I'm going to use it here is according to these principles, where I would say that a cloud-native data storage format leverages existing cloud storage systems such as S3 or GCS for scalability while avoiding any service maintenance burden. I would say that services like S3 or GCS in particular, compared to other cloud storage systems like Bigtable or Spanner, are unique in that there's really no there's sort of no concept of explicit number of servers that are being used to serve the data. You just can write the data, read the data, and you pay by the amount of data stored and the operations performed. But you don't have to worry about the scaling that essentially happens automatically. Now, that in itself, in order to be able to leverage these systems, there's some more important properties that a format needs to have, which is that you basically need to be able to do whatever relevant partial reads or queries that you would like to do just by doing byte range requests on this, on whatever data is stored on this storage system. Some sort of traditional database format that might rely on a lot of scanning and sort of filtering of data as you read it is not going to work very well if your only interface to the data is through a relatively low throughput, high latency storage system. And in particular, we would like to have efficient access, ideally directly from a web browser, even over such a high latency link. And then something that goes along with the scalability that we might hope to get from these cloud storage systems like S3 or GCS is to be able to do a large number of concurrent reads and writes for many machines. The concurrent reads basically comes for free if you just have scalability, but supporting concurrent writes does also require some care in the design of the format. And so, there are a number of formats that, there's the Neuroglancer pre-computed format that's evolved in several ways. There's N5 and there's R. I think Neuroglancer has certainly pioneered the reliance on these formats for sort of scientific data visualization. And for the particular case of a lot of the public data releases that we've done, by using these sort of cloud native data formats, we can essentially release a data set in a way that allows interactive visualization and querying just by writing some files to a storage system, and then there's basically no ongoing maintenance. We don't have to keep, we can release a data set several years ago and basically have to do no ongoing maintenance of some service to keep that data set available. And that's a pretty important property for sort of archival data storage, where it's really not feasible to keep some complex serving stack maintained over the years as you move on to other projects, but still would like the data to be available. All right, now I'm going to move on from these sort of general principles of Neuroglancer to give an overview of the sort of overall design. So at a high level, in Neuroglancer, there's this concept of a user layer, which is sort of, it's intended to be similar to like a layer in Photoshop or in a CAD tool, where it sort of corresponds to one logical type of, sort of one logical sort of data modality or something. It might be a particular image volume, a particular segmentation of that image, or some type of annotation on top of the data. These layers are made up of usually one, but possibly multiple data sources, which could be in a variety of formats, like the pre-computed format from the Google Brain Maps API, Divid, Mazar, N5. One case where you might have multiple data sources making up one logical layer is where you have a volumetric layer and also a mesh. You may have a volumetric data source and then also a mesh data source that you wish to present as one logical layer. Volumetric data, mesh data, and skeleton data all as a single logical layer. These sort of logical user layers, based on these data sources that are added to them, then produce, or essentially then correspond to a larger number of render layers, as they're called in Neuroglancer, where these render layers correspond to sort of a specific way of rendering a data source. And so, for example, from a image user layer, we may then have an image cross-section render layer, or an image volume rendering render layer that provide different views of that same data. or similarly from a segmentation user layer, we have a mesh data source. We may then produce a mesh render layer. So these render layers, in addition to depending on the view parameters, also basically work in terms of chunk sources that are provided by the data source. So in Neuroglancer, all of the data that ultimately gets rendered is considered a chunk. So it's sort of broken up into pieces of different sizes. For a volumetric layer, a chunk would correspond to a rectangular region of the volume, like 64 by 64 by 64 at a particular scale. For a mesh data source, a chunk is going to be a particular fragment of the mesh, usually corresponding to a particular subregion of the volume. And so the render layer makes use of these chunk sources. And then finally, there are these views. So, in a given Neuroglancer viewer, we might have multiple cross-section views, multiple projection views. And so these each of these views essentially pulls in all of the render layers that are compatible with that view type. So a cross-section view will consider only like an image cross-section render layer or a segmentation cross-section render layer, but ignore any mesh render layers. And similarly, a projection view will look at the mesh render layer or a skeleton projection render layer or an annotation projection render layer, but ignore the image cross-section render layers. And so the sort of the overall architecture of Neuroglancer is oriented around this rendering pipeline where we have we essentially have state changes that are triggered by user interaction. Based on these state changes, there's a chunk worker thread that's sort of constantly recomputing priorities for chunks to download, initiating downloads of chunks, decoding those chunks, and then transferring those into the GPU memory. And then in parallel, we have a main rendering process, which is essentially just computing which chunks need to be rendered, checking if they're present, and if they are present, rendering them. And so the overall idea is that sort of in the ideal case, we can have data coming in at a fairly rapid rate with minimal processing, getting uploaded to the GPU, and then getting rendered. So, as I just touched on, in order to support this overall rendering process, Neuroglancer uses a number of different threads in parallel. There is the basic constraint, because Neuroglancer is a web application using this mechanism called WebGL to do rendering. It is unfortunately constrained to only interact with the GPU from the single main UI thread. And so that main UI thread does need to do all of the rendering, and it also unfortunately needs to deal with all of the uploading of data to the GPU and downloading of data from the GPU. And so in order to minimize the blocking of this main UI thread, which by the way also needs to deal with all of the user interaction, we try to move essentially everything else off to other threads, or everything that's expensive. So this main UI thread deals with configuring of the data sources and downloading data source metadata, which is small and inexpensive. It also determines which chunks are visible, and then does the actual rendering. And so, as user interactions are happening in this main thread, it's constantly sending state updates to this closely tied chunk worker thread. And so this chunk worker thread is what's responsible for sort of managing the prioritization and downloading of all of the data required for rendering. And so yeah, so this thread, so actually on the main UI thread, we're actually computing visible chunks and then rendering those chunks. On the chunk worker thread, we're actually duplicating some of that work just to avoid having to coordinate between them. So it's also computing visible chunks. But in addition to visible chunks, it's determining which chunks are, should be prefetched. And then also, in addition to just determining which chunks, it's also assigning a priority to them. Whereas in the main UI thread, we're just determining the visible chunks, but aren't concerned with priorities. And so originally there was just a single main UI thread and a single chunk worker thread. But then it became clear that this chunk worker thread was getting bogged down by expensive decoding, like decoding JPEG formats, decoding other compressed formats, and decoding meshes. And so we added this additional pool of threads for specifically decoding chunk data. And so now we have this chunk worker thread that initiates downloads, but then separate threads actually do the decoding and then send the decoded data back to the chunk worker thread. And then the chunk worker thread is responsible for determining which chunks actually should be uploaded or to GPU memory or evicted from GPU memory, and then sends those updates to the main UI thread to actually perform them. So the one thing to note is that this chunk worker, this sort of chunk decoding worker thread, the chunk decode worker thread pools, the chunk decode worker threads, they operate relatively independently through a fairly simple API. They receive essentially a request to decode, do a particular decoding operation, they do the operation, they send the result back. So that's sort of a very simple form of basically stateless interaction between the two, between this chunk worker thread and the chunk decode threads. In contrast, the interaction between the main UI thread and the chunk worker thread is quite complicated because the main UI thread essentially sets up all of these data sources and layers and views, but then needs to but then the chunk worker thread also needs to be aware of all of these data sources and layers and views because it needs to sort of do the same visibility and prefetch calculations based on those views and data sources. And so we essentially have a sort of mirroring of state between the main UI thread and the chunk worker thread, where there's sort of a corresponding object in the main UI thread and in the chunk worker thread. And so that does unfortunately introduce a lot of complexity to sort of manage these coordinated states between the two threads. But that's difficult to avoid because of the constraint that all of the GPU interaction has to happen from the main UI thread. And then to touch a little bit more on how the actual data downloading and queuing works. There's essentially a unified queue system for all of the data managed by Neuroglancer. And so initially, any sort of piece of data that's needed for rendering, or if it's not already managed, so initially there's no record of this data, and so it would be considered unmanaged. And then as soon as something requires this piece of data, it enters this queued state where it's not yet loaded, but we're tracking its priority, and so that it gets a priority assigned based on, for example, if it's a visible chunk, lower resolution data gets higher priority, so that it sort of Neuroglancer will first load the coarser data before loading the finer data. There's similar priority rules for other types of data, and so all of these chunks that are required end up in this queued state, and then based on the priorities, if there are available download slots, chunks will be moved from this queued state to the downloading state and begin downloading. Or if there's chunks that are queued that are higher priority than chunks that are already downloaded, then the already downloading chunks will actually be evicted and replaced by a higher priority chunk. And then once a chunk completes its downloading and decoding, it moves to this state where it's stored in system memory. And then there's a similar prioritization mechanism whereby chunks get moved from system memory, which is sort of, there's a fixed limit on the amount of system memory that Neuroglancer can use, but this limit is usually larger than the limit on the amount of GPU memory Neuroglancer can use. And so there's a similar prioritization for chunks to move from system memory to GPU memory, because GPU memory is where they have to be in order to actually render them. And then likewise, if a higher priority chunk needs to be rendered, then it may evict something, it may evict a lower priority chunk from GPU memory back to system memory, or out of the system entirely back into the queued state, if we don't want to even keep it in system memory. So this sort of unified queue mechanism is what underlies essentially all of the data management in Neuroglancer. There's some, so on the whole, I would say it has worked fairly well. It's, initially there wasn't actually any prefetching really supported in Neuroglancer, but just because of this behavior, prioritizing lower resolution data, you sort of got a form of prefetching for free as you move through data, because as you keep moving along a given direction, the highest resolution data may not be available, but there would usually be a lower resolution lower resolution level already loaded for the given viewport. Yeah, at a later point, we did add prefetching, where for a given view, there was sort of an estimation of the velocity in a given direction based on a exponential weighted moving average, and then this is used to sort of assign priorities to non-visible chunks as well to prefetch them. All right, well, so I've given an overview of the sort of overall design principles and some of the architectural details of Neuroglancer. So I'll move on to touching on some of what I think are the interesting GPU programming challenges that have come up in Neuroglancer. At a high level, a key challenge with Neuroglancer has been overcoming the limitations of WebGL and WebGL2. Now, in most cases, you're running Neuroglancer on a desktop browser, which has probably has a reasonably powerful and presumably modern GPU that's presumably capable of fairly general compute interfaces. But WebGL and even WebGL2 are sort of based on this lowest common denominator of sort of mobile GPUs from previous generations. And so is much more limited in the APIs that it supports, particularly as far as compute APIs. So in many ways, even though we're sort of decades past it on the sort of native application side, dealing with WebGL has a lot of similarities to the early days of general purpose GPU computation before things like CUDA came along, where we have to sort of shoehorn what we want to accomplish into we have some general computation that we want to perform, we have to shoehorn it into very graphics-oriented things. So from the GPU side, rendering triangulated meshes is actually about the simplest thing that Neuroglancer supports, because that's sort of very much fitting with what these graphic APIs are designed to do. Whereas rendering volumetric data is taking us quite far from the sort of typical way these APIs were intended to be used. It ends up being much more challenging. So the original version of Neuroglancer was based on WebGL1, because at the time that was the only API that was widely supported. And in WebGL1, integer operations are actually not even available. And so, for something like rendering meshes, you can get by pretty well with floating point. But when we talk about doing things like decoding compressed formats, or dealing with where we have logically maybe a 1D or 3D or 4D data set that we've somehow packed into a 2D texture by tiling it, it's very critical to have precise integer addressing and precise integer operations. But those were not actually supported by WebGL1, so we had to emulate them with floating point operations, and that was, by itself, okay, it's a little annoying, but like you can think of a floating point, a 32-bit floating point number as like a 23-bit integer, so it should be okay. But there's the added challenge that in WebGL1 implementations, we're also allowed to do all sorts of like mathematically unsound optimizations. So they can change orders of operations, use lower precision operations, and so there was sort of this constant struggle as Neuroglancer was tested on new drivers to sort of fix any issues that came up with sort of insufficient floating point precision corrupting our integer operations. Now with WebGL1, there was actually only 2D textures. With WebGL2, there are 2D and 3D textures, but logically we might have 1D data, like a hash table, or we might have greater than 3D data, like we might have a 4D, 5D volume, for the the compressed segmentation format used by Neuroglancer. It might be logically just basically a stream of bytes, but in order to use it from WebGL, we still have to pack it all into a 2D or 3D texture. But that can mostly be handled. You can just there's different ways of packing it in, but it can be done. There's an interesting challenge as well. So one of the things that was added somewhat recently in Neuroglancer was the ability to compute and show histograms of the data. So for dealing with like uint16 volumes where you have a large dynamic range, there's a need for the user to be able to sort of tune the min and max values that are used when mapping this data to colors on the screen. And by showing a histogram of the currently viewed data, that makes it a lot easier for users to choose appropriate bounds. And by itself, computing a histogram is like a lot less expensive than rendering the entire data set. But if we had to like somehow copy this data back to the CPU or do this histogram on the CPU, it might end up being quite expensive because, again, with JavaScript, we're sort of limited in our CPU power. And so it is possible to compute a histogram on the GPU, but one of the fundamental parts of computing a histogram is this scatter operation where you're basically summing up for each bin the number of points that falls in that bin. And so there's actually only one way to do this type of scattering operation on the with WebGL, which is basically to do it by rendering points to like a 1D texture, where you basically have to just basically each sample becomes gets translated into basically the value that you want to contribute to the histogram gets translated into a position that then gets mapped to a position on this output texture that you're writing to, and then you can use additive blending to sum up the samples. So that's just one trick that was interesting in that regard. One of the issues that came up very early with Neuroglancer was the large size of uint64 volumes. So at Google, we've been using 64-bit integers to represent all of our yeah, to represent sort of all of our segment labels. Initially, we probably could have gotten by with 32 bits, but certainly as we've gotten to these larger segmentations, that wouldn't be sufficient. But in any case, we had been using 64 bits regardless. And if you consider just like a single, full HD monitor size view of 1920 by 1200, and you want a cross section, you want to display a cross section of this size, and you're using, say, 64 cubed chunks of data. So already that's going to be 1.2 gigabytes just for the data for a single view on the screen if that was stored uncompressed. So this was, in Neuroglancer, the default GPU memory limit is 1 gigabyte. And so sort of just showing that, already just a single screen full of unit 64 volume would be too large to fit in memory. And so there was a need for this compressed segmentation format that would allow the memory to actually, it would allow the segmentation to actually be compressed when it's stored in GPU memory and allow us to render directly from this format. And so essentially one of the key properties that you need for a format to be, basically a compression format to be renderable, is that it allows random access to every location independently. And so a format like JPEG, where you have basically, with JPEG, you have every 8x8 block of pixels sort of encoded together with this discrete cosine transform representation. But basically what that means is you can't read the value of a single pixel in that 8x8 block. You have to decode the entire 8x8 block at once in order to do that. And furthermore, well, so JPEG also uses an entropy encoding for these, for the data. And so entropy encoding is definitely not compatible with like accessing a single pixel at a time. And so this compressed segmentation format that I devised was designed specifically to allow us to do this random access. So we have every block of data, we break up our larger, say, 64 cubed chunk into smaller blocks of like 8 cubed. In each of these 8 cubed blocks, we determine the number of unique IDs, and then based on that, determine the number of bits that we need in order to represent the number of distinct labels. And so then we can have a header at the beginning of the format that specifies the number of bits required for each of these smaller blocks, and then the offset for the encoded bits, and the offset of the lookup table that maps basically each of these smaller numbers to the actual value. And so this format basically allows us to, assuming we have a lot of locality, spatial locality in the labels, this allows us to greatly reduce the number of bits required for every label, while still allowing a relatively small number of, we can compute the label at a given position with a relatively small number of operations. So another challenge that came up in Neuroglancer is we wanted to be able to very quickly, as you're moving the mouse around selecting segments, we wanted to be able to very quickly change which segments are appearing to be selected in the cross-sectional views, apply various color maps, equivalences to them, without having to rewrite and sort of re-upload all of the data to the GPU and do a lot of CPU processing as this changes. And so, one of the very simple and common strategies used for doing some sort of mapping like this on a GPU would be to just use a lookup table. If your labels were all like 256 byte, 1 byte in size, you might have a very small 256 element lookup table that maps each value to like a color. And then if you want to change the color mapping, you can just update this small lookup table. Here, though, we have an ID space that might be 64 bits, which is much too large for a lookup table. And so doing this remapping on the CPU, as I mentioned, would require a lot of additional copying that we want to avoid, particularly because due to the way web browsers work, there's sort of extra latency with sending data to the GPU because the GPU rendering is actually happening in a separate process from the main JavaScript evaluation. And so what we use instead is a hash table, which is sort of your go-to answer for doing this type of mapping on a CPU. There's the interesting constraint with GPU programming that we don't want to have to do a lot of divergent work at different locations in the image. And we also don't want to have potentially high latency. So with a regular hash table, typically you sort of, on average, you have to do a small number of lookups, sort of a small number of sequence of lookups in memory to find the key that you're looking for. But in some cases, you do have to do a potentially unbounded or almost unbounded number of lookups to find the key. And so with WebGL1, there was actually a constraint that all loops are basically have a constant bound. With WebGL2, that constraint is relaxed, but for efficiency, it's still better not to have these sort of divergent loops going on in a GPU computation. And so there's actually a type of hash table called cuckoo hashing, which is well suited to this because cuckoo hashing lets you, depending on how you construct it, you then have to do only a constant number of lookups to find a key. So typically either 2 or 3 lookups to find the key. And so this is very well suited to doing this lookup directly on the GPU. All right, now I'm just going to move on to some of the lessons learned through the development of Neuroglancer. So I'll say first some things that have worked well. So offloading computation to the GPU has generally worked quite well. Being able to sort of do all of this mapping and computing arbitrary cross sections directly on the GPU has allowed Neuroglancer to offer quite good performance despite the limitations of web browsers. One of the early decisions made in Neuroglancer was not to rely on other existing libraries. Like there's a library called 3JS, which is widely used for sort of doing graphics in web browsers. But for a tool like Neuroglancer that's doing things that are very performance sensitive and sort of very outside the realm of sort of normal graphics, I would say, it was important to not have something in the way of standing in between Neuroglancer and the underlying primitives offered by the web browser. So what this does mean is doing things like drawing lines is actually quite challenging. And so there was sort of a surprising amount of effort that goes into just drawing lines and bounding boxes and things like that. But it does mean that once we have that implemented, we can draw hundreds of thousands of lines quite efficiently without a lot of overhead. And sort of likewise for doing things like doing the volumetric rendering, we don't have some intermediate layer that's getting in the way of that. One of the challenges that comes up with GPU programming is testing. It's not possible to do any logging inside of a GPU shader. And so there's sort of this common, often people sort of resort to like debugging by looking at the output and, hopefully it's not like all black and guessing what's going on or modifying their code to output certain colors to try to, send a small amount of information back. So that's quite tedious. And so somewhat early on with Neuroglancer, we set up basically a unit test framework that allows us to execute shader operations with sort of fixed, with some variable number of numerical inputs and outputs. and the framework takes care of transporting the inputs into the shader and getting the outputs back out. And so that allows us to have sort of unit tests of these complicated operations like hashing or decoding of the compression format without having to rely on these sort of very difficult debugging techniques. Using so exposing this OpenGL shader language directly to users to allow them to customize rendering, that was sort of a very kind of a trick that allows this sort of very powerful programmability with very little work on the part of Neuroglancer. On the whole, that I think that was quite successful. Allowed people to customize their rendering in very powerful ways with some minimal work. I think trying to maintain this abstraction of data sources has also worked well for Neuroglancer, and in particular by sort of looking at what operations and sort of what abstractions are applicable to multiple data sources has sort of helped refine what those abstractions should be in the first place. So there's a number of things, number of design choices that have proven to be problematic in Neuroglancer. So in Neuroglancer, we have this, we have constant state changes. We have, we have segments being selected. We have positions changing. We have data sources being added, and so on. And so the way Neuroglancer handles this is through this signal interface, where signals are defined and callbacks or different components add callbacks to be called when this signal indicating some type of change happens. And basically this management of the callbacks has to happen manually and tends to be pretty easy to get wrong. Some time ago, I learned of this library called MobX that provides a different abstraction for this type of signal handling, where instead of manually adding callbacks, there's this sort of automatic tracking of sort of which pieces of state are accessed during certain types of operations, and then automatically sets up notifications for those operations to be rerun when that state changes. And so this is something that I would be keen to, this sort of more automatic management of state change signaling is something I'd be keen to add, although retrofitting it into Neuroglancer now would certainly be a large task. There's sort of a similar manual operation that has to happen with reference counting. So in JavaScript, there's a garbage collector, which means normally you don't have to sort of manually keep track of sort of ownership of objects. But with Neuroglancer, as I mentioned, we actually have this complex interaction between the main UI thread and this chunk worker thread, where we sort of have a lot of objects that are sort of represented in both threads. And so in order for that to work, we can't rely on the garbage collector anymore to sort of operate across this boundary. And so instead we have to use reference counting, and that requires a lot of sort of manual tracking to update the reference counts. Now, I'm not sure there's a better alternative for that reference counting, but one thing that Neuroglancer lacks is sort of comprehensive unit tests of this reference counting, which does mean there's potentially a number of bugs lurking around that haven't been addressed. One of the big issues, performance issues in Neuroglancer is the fact that right now every chunk is stored as a separate texture, which in practice means every single chunk, like every 64 cubes of data that we render, requires a separate draw call from JavaScript. And these draw calls are pretty expensive, and so that means if you have a very large number of chunks being displayed at once, the performance suffers. In games, there's a common technique of tiling where you might have a single texture that stores a whole bunch of tiles, and then you can organize things so you can have a single draw call that basically draws a bunch of stuff. So this is a little bit challenging to implement the same thing in Neuroglancer, because in a game, your sort of data that you're working with is probably fixed for like an entire level. So it's easy to set up a single tiling that will work. In Neuroglancer, the sort of data is constantly changing. And so you could imagine, we would essentially have to implement our own memory allocator to sort of fit the data into textures as we're loading and unloading it. And then there's the additional challenge that for things like the compressed segmentation format, not all of the, the actual space occupied by a given chunk is variable, depending on how well it compresses. And then there's the additional challenge that, we have potentially many different types of layers, and they all have different data formats, and we can't just stick them all in the same texture, the same type of texture very well. So to do this with the current WebGL, we would have to maintain basically a bunch of different of these textures as separate allocation pools, and so that complexity didn't seem worth it. Moving forward, there's a new web GPU programming API called WebGPU that provides sort of more general ways to deal with memory, and it could potentially make that more feasible. I think we're running a little low on time, but I will talk about one more major point, which is that I've always been a little bit, the documentation in Neuroglancer has always been rather lacking, unfortunately, and so while that still hasn't prevented the tool from getting a lot of use, I think it has meant that there's a lot of functionality that many users are just unaware of. And so I think focusing on improving the documentation is definitely something that I would like to do going forward. I won't talk about those remaining few points, but I'll just briefly talk about some future directions. So, as I mentioned, there is this new web programming API called WebGPU that potentially provides much better support for general computation or general memory management. And so, this is not widely supported yet. And in practice, it wouldn't be reasonable for Neuroglancer to make use of it until it can fully migrate to it, because having both a WebGL implementation and a WebGPU implementation would be pretty impractical. But certainly, in the next year or two, that's something hopefully we can migrate to. Something else that I think could be a very interesting direction is better integration with annotation databases. So right now, Neuroglancer supports a few sort of somewhat limited annotation databases. There's the Neuroglancer pre-computed format, which is read-only, which sort of supports some functionality, but the sort of querying is kind of limited. Then there's there is actually support for the Divid annotation, Divid annotations, but I think going forward, it would be very interesting to have sort of more general annotation database support. For example, being able to just have annotations in a Google Sheet and then read and write them from Neuroglancer, and then sort of by relying on Google Sheets, we can sort of potentially have automatic shared annotations in Neuroglancer. Likewise, being able to just read from a SQLite database and view that as annotations, or doing more advanced querying where you have a query language that's integrated with Neuroglancer state. Finally, I think while it's sort of a fundamentally pretty simple feature, it would be nice to be able to use Neuroglancer for applications where you would like to do hand labeling of volumes as well. So that's something that hopefully can be added in the future. All right, well that's it for future directions. So I see I'm running a little late, but if anyone has any time to stay around and any more points that want to be discussed, I'm opening it up for discussion now.
Thanks very much, Jeremy. That was very informative, and I definitely appreciated kind of like the low level approach, so that because a lot of people I think on this call are already pretty familiar with the high level Neuroglancer, whereas this stuff was very interesting to me. So before we get into questions, I just wanted to ask you, how much time do you have? We're kind of open-ended here, and we'll eventually upload all this stuff to YouTube for future, reference by people who can't attend the whole talk.
Yeah, I mean, I don't have any. Yeah, I can stick around for a little while. Yeah.
Okay. So we'll start. I'll start asking people to ask their questions. I've got a bunch of questions, but I'll wait. And so I'll just go by my screen. Philip.
Thanks for the talk, Jeremy. What are your thoughts about WebAssembly?
Yeah, that's a good point. Yeah, I mean, so when I started Neuroglancer, WebAssembly wasn't really a thing. So that wasn't a good good option. But it's certainly it's certainly true that you could imagine now a version of Neuroglancer that's primarily implemented in WebAssembly. I think one of the difficulties now with WebAssembly is that there's still not a great story as far as interacting with browser state. And so you sort of have WebAssembly, which is operating in its own sandbox, and actually manipulating the browser UI or even doing GPU operations is a little bit expensive now. It's actually more expensive from WebAssembly than it is from JavaScript directly. And so that's sort of yeah, so there are actually a few components of Neuroglancer already using WebAssembly, like decoding of certain compression formats. But yeah, certainly it could make sense to sort of move a lot of the data management into WebAssembly. But I think that would be more compelling, and once there's sort of a better story for interacting with the browser from WebAssembly directly more efficiently. I think the Web GPU group is attempting to do that, of providing sort of high performance interfaces for using Web GPU directly from WebAssembly.
Okay, thanks, Davis.
So in the previous slide, I think there was a reference to the pixel center, voxel center. Yeah, yes. The origin. So why was that an issue?
Yeah, so I think, so originally, yeah, so basically in Neuroglancer, well, okay, so yeah, as probably many of you are familiar with, you have this, this sort of, when you deal with like mapping pixelized data to a continuous coordinate space, you have this question of, what is the, in continuous space, like what is the 0, 0, 0 in continuous space? Does that correspond to like the top left corner of a pixel or to the center of a pixel? And so, in Neuroglancer, I made the decision without thinking about it too much initially that the top left corner, yeah, basically 0, 0 in continuous space by default basically corresponds to the top left corner of a pixel. So that kind of means that if you're looking at, if you sort of look at your data, you can imagine you have this, you can look at like the 0, 0, 0 point of your volume, and basically your volume begins exactly at that. If you're sort of rendering, basically your volume begins exactly at that cutoff line. Whereas if you say that like 0, 0 in continuous space is the center of the first pixel, then basically your volume actually would kind of start half pixel before that point. And also if you start talking about multi-scale data, now your lowest resolution data starts, or your finest resolution data starts like half a pixel before your 0, 0 point, but then you would kind of say that it's sort of, but kind of depending on what the resolution is, it actually would be sort of amount that it starts before the 0, 0 point kind of varies. So it seemed more natural to just make the origin the the top left corner. But initially, basically, the coordinates were still sort of being snapped to integers. So like if you move forward, if you like type in an integer coordinate, like you want to go to position, 100, 200, 300 in your volume, Neuroglancer would go there. And so then it would go to exactly that coordinate, which meant that you were actually located at the at basically the top left corner of a pixel, basically on the boundary of 2 pixels. So in a given cross-section view, it's not really a big deal if you're exactly on the boundary of 2 pixels. Doesn't make any difference. But when you start looking at different cross sections, now it's kind of a problem because it's a little bit undefined. If you say you're exactly at position 5, and then you look at a cross section, are we going to be displaying cross section 5, or are we going to display cross section 4? And so sort of, when we've typed in 5, so we actually want to see cross section 5, but to actually ensure that we are displaying cross-section 5 rather than the previous one kind of depends on sort of having our floating point numbers precision being exactly precise, which isn't feasible. And so, whereas if we would say that we're going to be at pixel, if we're at position 5.5, it doesn't matter if our number is a little bit imprecise because we're still going to get the right cross-section. So, yeah, so this sort of was a little bit of an issue. Initially I did try to solve this just by, making the precision better and trying to avoid precision issues, but ultimately realized that was kind of a bad direction to go, and instead just changed it. So basically you type in coordinate 5, but actually Neuroglancer positions you at 5.5. And so, so that sort of solve that issue. So basically by changing it so the Neuroglancer will snap to the half pixel rather than to the exact pixel boundary, that solves that precision issue, while still sort of keeping the coordinate system the same for backwards compatibility reasons.
So do you think things would have been easier if a pixel is assigned to the middle of what it looks like when it's rendered as a square, as opposed to the corner?
Yeah, I'm actually not.
Pixels don't have an area, or like data points don't have an area. They get rendered as a geometrical object that has an area, but as a point, it's just a point.
Yeah, I mean, I guess I feel like with EM data, especially when we start dealing with segmentations, or at least I did have the mindset of a pixel. In practice, we usually did view the data without interpolation, so a pixel is shown as a square, and especially with segmentations, there's no interpolation. So this sort of idea of a pixel as a square or a cube, whatever, that was sort of the mental model I was coming into this with. And I guess in terms of this in terms of this. And sort of in terms of how the downsampling is typically done, it also seemed to make sense to sort of treat them as the top left corner. But certainly I think this issue of like snapping to, definitely the sort of snapping to the exact pixel boundary, that was a mistake. Whether it would have been better to use the center as the actual continuous origin, that's something I'm not sure about still.
Okay, we're going to get a few more questions in here. One question that I had, Jeremy, was if you can go back to your threaded architecture slide, where you had the different boxes showing, this particular thing. So down in the chunk decode worker threads, when you were talking about compressed segmentation and coding, and you kind of covered that in a later section talking about, the Neuroglancer compressed segmentation format. And I know that you had mentioned to me before about like that being kind of necessary for optimal sort of GPU memory usage. I guess what I didn't know before, you can clarify this. So if you're essentially using various data sources and you're asking for compressed data and they're coming in kind of like a UNT64 volume or some kind of, random thing. Like I think, like for example, the Compresso method from the Sun Lab or one of these other compression algorithms. Is your shader code kind of reliant on the Neuroglancer compressed format such that you have to kind of do transcoding?
Yeah, so actually, it is possible to render directly from an uncompressed volume. There is support for that. At the moment, there's basically two chunk formats that the underlying rendering code can support: uncompressed and the compressed segmentation. But yeah, so if the, basically this memory issue does, if the data comes in uncompressed, that's kind of unfortunate, but we do actually then in most cases transcode it to the compressed segmentation format before loading into the GPU so that it doesn't take up too much GPU memory, because otherwise, we would have that same issue where, compressed, the data might be fairly small, so the network transfer isn't too bad, but then it gets blown up when it's decompressed. And so then we have to compress it again to reasonably fit it on the GPU.
So if someone wants to add a new segmentation compression algorithm, like maybe the Compresso team or whatever, do they go in and then write the shader code in order to make sure that there's no transcoding? It essentially just moves it to the GPU and they can access it directly there?
Yeah, I mean, that would be nice. I mean, I think the Compresso format is not really oriented to support like direct rendering.
Yeah.
So yeah, there's not a lot of, so far there hasn't been like another format that has been designed to support direct rendering. I think the format that you devised for Divid is one that could support direct rendering, so that is something that we could potentially support.
Right. Okay, cool. And I think Philip had another question.
Yeah, sure. I believe that Neuroglancer uses multi-resolution to support progressive refinement. So you quickly see low resolution chunks and then higher resolution versions as time goes along. Does it also support a level of detail idea, sort of like in a flight simulator or a game, where something that's far away from the view and not prominent will never go above the low resolution?
Yeah, for meshes, there is a, basically for meshes, there's a sort of, so for meshes, there is a computation of the desired resolution, which is sort of based on the effective magnification that chunk would be shown at on the screen. So like, so if you're using a projection rendering, then yeah, stuff that's far away will sort of have effectively a lower magnification, and we'll choose a coarser resolution for the mesh. If you're using orthographic rendering, that's not going to happen. So yeah, there could be room for some improvement, like to try to decide if, somehow prioritize that, although it's a little more challenging, so I haven't done that yet.
Okay, I guess I'll ask another question about the JSON state format. That's definitely, I think, one of the great features of Neuroglancer, such that you're able to give state to, just have a link so that everyone can see exactly what you're looking at. But you had mentioned that due to the backward compatibility and how that kind of stuff evolved, looking back upon it, would you think about doing it differently, or do you think there are lessons learned about state and the transmission of state and how you might go about that now?
I mean, I guess you could, I think originally, in part, I imagined it being more readable directly in the URL bar than it ended up being. Like I went to some gymnastics originally to like encode, to sort of choose. I mean, you can almost dump the JSON directly in the URL But yeah, in order to make it sort of still appear like a valid link to various things like email clients or whatever, you have to limit the characters that are used. But originally I did some gymnastics to try to make the more preserve the appearance of JSON so that you could kind of read it directly in the URL. So yeah, there was sort of a specific choice of JSON to make it, to sort of try to make it easy to interact with directly. But then as as time went on, these sort of special, more readable encoding proved problematic. And so we moved to sort of more traditional percent encoding that makes it pretty much completely unreadable, but then added the little curly brace icon so you can just edit it directly in Neuroglancer. So yeah, I mean, given that it's not readable in the URL anyway, you could imagine using like proto buffs, which are sort of more specifically oriented around backwards compatibility, or gzipping it or whatever, ZSTD, compressing it so that it fits better. I'm not completely sure. I mean, I think JSON is sort of very accessible. It's a lot more accessible than like proto buffs that sort of add kind of some nuisance to interacting with from various programming languages. So I'm not sure if that was if that's something that I'd recommend changing. But definitely, I didn't, going into it, I didn't always, starting out, think through the design choices as far as the state as carefully as I could have. I didn't sort of think through all the backwards and forwards compatibility implications.
Well, thank you very much, Jeremy. It doesn't look like we have any additional questions. And since we're already over time, I mean, we could continue on here talking about so many different things, I also don't think like you covered the movie making stuff that is available on Neuroglancer, though even we covered that slightly in our previous week. So it would be interesting to see if you can't document all the really cool new features in Neuroglancer, sort of in a complete level, that it would be interesting to have like a page where it just describes, just a bullet point or something. Might even call for volunteers to, hey, given the fact that this does exist and is poorly documented, will someone volunteer to, go and update the documentation or do something and contribute back to the project? I think Napari does something like that, does a pretty good job of engaging with the community to try and pull in resources. Yeah, but I think so. Anyone else have any questions, thoughts? Okay, so I guess we'll wrap it up, and thank you again, Jeremy.
Yeah, we'll say on the documentation front, that is something that yeah, I'm trying to find some time. I've started to put together a framework for sort of scripting tutorial videos, because I think a lot of the functionality in Neuroglancer is sort of best described in terms of a little demonstration rather than just a textual description. So I've started to put together a framework for sort of scripting these sort of tutorial type videos. And then, that's something where once sort of this framework is set up, could potentially get some community contributions for covering all the different functions. But I haven't found time to complete that thing first. But.
Okay. Thanks again, and I'll look forward to seeing everyone again in 2 weeks when we talk about DataViz and HiViz 2.